Welcome back. We're ready to start. And welcoming up to the podium all the way from Austria, Petra Gruber.
Thank you very much. So first of all, I would like to thank the organizers for having me here. It's very kind. I'm super happy to be back and catch up with friends and colleagues and see other people's research developing in a good way. So I have worked at the University of Akron at the Brick Center for 5 years. I've returned back to Austria 1.5 years ago, and since then do, again, projects in architecture and biomimetics in my own company, Transarch. And since last winter, I've transitioned to the Austrian Research Promotion Agency and switched gears to research funding. And I'll talk a little bit about sustainable strategies for emission-free transportation in Austria. And my talk today is about, as I said, bioinspired design and sustainable mobility, and will comprise a bunch of projects after I'll introduce you to the framework of my work. And the projects are kind of tied together and followed like one after the other, kind of inspiring one another until we had a research project in Austria that we started just last year, the Biocool, which is the last in the series that I would like to show you today. I probably have too many slides, that's why I'm talking so fast. So we'll see if I have to jump over something. And so the frame of my work is to go into the direction of a living architecture. So I look at architecture and the built environment in general through the lens of biology, using the science of life or criteria of life as a framework. And this is also what my PhD was about. And it's really interesting for me that this concept is still a valid one for my work and my projects. And this means that I use those categories like order, propagation, growth, energy use, reaction, homeostasis, evolution, to look at the built environment on a variety of scales, from the really detailed scale over materials to building scale to urban design and regional planning scales. And what it is essentially about that we need to shift towards an architecture that's more dynamic, responsive, adapted, differentiated, and so on. It comes closer to living organisms. And for our technical systems, it means that we need more interaction with the environment. We need to think about water cycles and so on. So all those issues that you have heard in the last 1.5 days need to be implemented and integrated in our architectural and building context as well. So the mission really is to work at this intersection of biology and architecture, use biomimetics to inform architectural design, and work in innovation in buildings and material scale. At least that's the case for myself. And also to work with new production processes towards sustainable design and targeting the quality of the built environment for everybody, but also for the non-human living environment. So the built environment is essentially what humans made a space in which people live, work, and recreate on a day-to-day basis, encompassing places and spaces created or modified by people, including buildings, parks, infrastructure, and transportation systems. So it includes transportation inherently in a way. So my work is essentially not about transportation directly, but what we are thinking about is how we can move people, how we can live, where do we have to be at a certain time. So where are our locations and how do they connect and interrelate spatially with each other? How do we work with materials and resources, and how do we manage those? And one thing that we were very busy about is like how is the material scale working? How do we work sustainably with materials? And what does that mean for the building scale? As I said, the built environment is essentially about all those scales of design, and the tools and frameworks for those scales are inherently different. So you cannot work on all of them at the same time. So I think you would also have to decide what you're focusing on. And another important piece of information is that humanity will essentially live in urban environments in the future. That's what it looks like at the moment. So we have reached the point where more than half of the world's population is living in urban environment. So this is what we need to think about if we want to make a big impact onto our future world, is to think about our cities and how we can sustainably develop cities further to a real good quality of life that could look like this. So this is a the outcome of a project that a colleague of mine, Barbara Imhoff, has worked on. And this is another futuristic vision that you have seen many of in the last 1.5 days. So what I've been really busy with is working on the energy side of buildings. And there's a lot of energy and also humidity and light flows through a building. So you can see here just a sketch that signifies that. So we are constantly busy with managing things flowing through our built structures. And what we are trying to do with biomimicry is to improve the situation. So I've worked a lot with a lot about bioinspired facade systems, for example, that are trying to manage the inputs and outputs through a building hull in new ways and in better ways than we usually do it. And one of the projects that came up in the last 5 years is the one that Ariana Rupp, one of my PhD students, worked on. And this is about the thermodynamics of leaf shapes and how that could influence the building of the future. And Ariana discovered that the shape of leaves is inherently influential in the thermodynamics. So this is known. So there's been some previous research about this. But we have looked at that in a biomimetic way. We have created a biomimetic setup and abstracted the shapes of leaves and looked at the evaporation efficiency to understand the impact of this shape functional connection. And what you see here is our very first crude experiments that looked at different shape abstractions. And we evaporated water through filter paper and looked at this through an IR camera. So you can see the temperature change. And by the temperature change, you can guess the evaporation speed. And this effect is really, really striking. You can also see this on other examples that we have, where the surface area is the same for all the models, and also the boundary length is the same. And you can clearly see that some of the models evaporate faster than others. And this is a very interesting effect because cooling is one of our big issues in architecture. So most people live in climates where cooling is necessary, and it takes a lot of our energy to cool buildings down. So if we found a way to be more efficient in cooling and in moving humidity around, that could be another a benefit and could save a lot of energy, and lastly would help us managing our planet within its boundaries. So after we had recreated this effect in the lab, we also tried to expose it to the outdoor, and we also tried to create a 3D system where we could observe this effect. And outdoors, it's much less, the results were much less consistent, because outdoors you have solar radiation that kind of overshadows all the effects that we had in the lab. So it's not a consistent result that we got. So we are still trying to find a way to recreate this effect in a 3-dimensional way for outdoor facades. So this is kind of the end point of Ariana's PhD. She finished last year, but the project kind of infused many other ventures after that. And another way to work with adaptability in architecture is to work with folding. So we had workshops on folding structures at the University of Akron. At the School of Arts, we invited a paper artist, Eric Scherde, for a folding class, where we collaborated and designed new solutions for technical designs together with the students. And what you see next is one of Thibaut's projects. You have met Thibaut in the morning. So this is another one of his projects where he tried to translate wing folding strategies from insects to building facade folding principles. And this was also published in a paper. And you see some of the design proposals here, and here these analysis pieces of abstraction, drawings, and also model making then to understand the effect and translate it. Another nice project was the one from Amelia. She tried to translate it into a fabric design. So students are really creative in taking up those ideas from biology and inventing something new. So this was one of my main tasks at the University of Akron, that I taught biomimicry there. And lastly, those two things, the leaf shape research and the origami principles that we worked with, were infused into a workshop that we got financed by the Humboldt University in Berlin, that was about breathing skins. So we worked with designers of different design students at the university there for a week with a 3D production lab. And we designed for like breathing skins for another way of adapting architectural design to make it more transparent for those energy and matter flows. So it envisions this kind of smart facade for architectural scale objects. And I collaborated with my colleague Lorenzo Giuducci about this, and many other people were involved. And the goal was, as I said, to go towards this direction of pursuing this analogy of biological skin that is really managing those flows, integrating passive mechanisms, being adaptive, and regulating thermodynamics. There's examples for this. There's NASA projects and other, movable facades that have been designed. And essentially, what we want to work with is using this paper modeling as a design research tool for functional shape change, and use this origami as a technological tool for developing innovation. And so there was a designed workshop flow. So we infused the students with knowledge from different sides. So they had these introductory lectures about origami, about biomimicry, about leaf shapes and plants. And then we experimented with those analogies and analyzed those principles further together with them, played around with paper models, did some experimental design. And lastly, we had a big phase with evaluating what we had done in terms of the goals that we had initially. And it was really striking that we had this very short week of time frame, but still we had, I think, about 12 successfully developed prototypes, folding prototypes that could then be taken further into a technological facade piece. So it was like on the way to develop an architectural solution. And we gave names to those projects, and I tried to record all the positives and negatives about them, and had a data sheet and information about each one of them. So you see here some of them more in detail. So this concept was a really weird one. We still don't know what to do with this. It has to do with this coiling up of drying leaves that a student tried to translate in a movable element. You can see it's very unstable. That's one of the negative sides of it. And then we had this very interesting one. So having curved creases is actually a really cool way of generating like these flipping motions that you can see. So this is something where you could have this kind of snapping movement that could serve for openings or closures. And we finally also used a new actuation methods of hydrogels to actuate the principles that we had. So what you see here is one prototype that worked with hydrogels that were embedded and wanted to use humidity to generate those openings and closings technically. So all sorts of really cool idea came out of this workshop, and we decided to evaluate the projects according to the parameters that were important for us. First of all, this biomimetic approach. We wanted to know, is it actually just a technological idea, or was there a real biomimetic idea behind it? Then what is the evaporation capacity of the project? And then lastly, what is the shape change capacity? So how far does the shape change go? And we made those big evaluation lists. And this is also something that came up in many of my projects, that you have many ideas and many proposals, and then you need to decide on how the heck are we going further from this? What are we doing with these 30 ideas? And those evaluation lists are always very tedious to make, but pave a way forward. So they really go through all the important parameters and then decide on what's really good about this project, what's really good about this one. And finally, you can come up with some kind of a ranking, and you can then decide which one to work further with. So here you can see the outcome of our project. You can see graphically which ones were best. And we also thought a lot about the technological transferability and which ones we could actually take further. And some of them were actually taken into the lab, and we followed some of them up with testing in the lab. But that was kind of the point where the project stopped. And as I said, a lot of people were involved in this. A lot of students collaborated with us, and we also had a glorious week in Berlin where we could work on this project together. Another workshop that was informed by Ariana's research was then a project that we did together with GAF, the big roofing company in the US, and they funded a workshop that we did at UA, where we tried to infuse this knowledge of the leaves with their products. So they have essentially, I think 95% of the products is asphalt shingles in the North American market, and that's what they were interested in to improve. And again, what we did was using the leaf shapes to generate fast drying shingles. So you can see here the setup. We just imposed the leaf shapes on the shingle shape, and they actually tried a lot faster because the boundary was longer. Apparently, there was an effect that is still trying to be determined physically in terms of basic physics. And so it showed us that we could actually use those differently shaped shingles to have a better drying roof and to have a faster drying situation there, especially in the critical zones of the roofs. So the assumption is that the faster you get rid of the humidity, the longer the roofs will last, and the longer it will hold up. And so we also did a lot of lab experiments here. And there's also a publication coming out now about this research too, in one of the books that were published by NASA too. So altogether, we can say that leaves as a bioinspiration is very useful for this heat and vapor exchanger design. And we were learning from these dissected geometries for evaporating interfaces, but there's still many, many unknowns that we have to uncover. Even the basic physics of this is still not entirely clear. And it's really great that the research that we did and the projects that we did then allowed us to go for a follow-up project that was funded by an Austrian agency. And we started a project that is called Biocool last summer, and it's located at the University of Applied Arts in Vienna and was taken over by my colleague Bernhard Sommer. And he's working at an institution that works for energy design, and our collaborator is the ceramics lab at the art school and the building physics lab from the TU Vienna. So it's really a great group of people to take this further. So what their mission is to take these ideas and further develop ceramic prototypes that take these ideas further and test it in a very controlled environment of the building physics lab at the TU Vienna, and also create an outdoor prototype of those wall topologies at the school. So the mission is really to explore the transfer of those morphological principles from biology to form optimized architectural surfaces for climate control of building envelopes. And so I'm really happy that this is running. It's still ongoing, so I can just show you some preliminary outputs. So what it essentially does is we want to design efficient evaporation elements for the building envelope. So it's about the morphologies, it's about this shape transformation, and it's about the integration into the building system. So there should also be concepts developed how those tiles are actually working. Is there water transport? Where's the water stored? What happens with the energy? How can it be transferred to the inside? Where is a heat exchanger and so on? And interesting is also the evaluation of the influence to the surrounding area in the urban space, assuming that a cooling facade would also have an impact to the surrounding area. So that's also something that's part of the project. And then there should also be a systems evaluation for different areas of application and climatic zones. So they also want to extrapolate those findings to other climates and areas and contexts. And those are essentially the questions that inform those work packages that I want to just jump over with. So what you see here are just pictures of the first prototypes. So they were working with different compositions, clay compositions, also using different colors, different kinds of clays, and they started printing those surfaces and also thinking about making a three-dimensional elements, and maybe also using internal channels to support the humidity flow in those tiles. So these are just the first images that I got from them, because I sadly handed over the project to my colleague because I got hired by the same funding agency. So I'll jump to the next part of my presentation today, talking about my work at the Austrian Research Promotion Agency. So this is a funding organization owned by the federal state of Austria, and it's processing funding coming from a variety of sources. And one of the main clients is the Austrian Ministry for Climate Action, BMK. And they are currently specifically interested to go towards sustainable mobility and to work on the transformation of transportation towards a sustainable solution. And they created the Mobility Master Plan 2030, and I want to present this briefly to you. So we are starting from the status quo to the current incentives that the government gives for e-mobility in Austria, and then briefly talk about the master plan that was designed. So what you see here is the number of battery electric vehicles that were kind of brought to the traffic in the last years. And you can see here that there was a tipping point mid-2020 when the rate was kind of getting much faster. And we had in September 2021, we had the highest share of electric cars in new registrations so far. And at the moment, I think it's every fifth car that is on the road is an electric car in Austria already. And we have more registrations for electric cars than diesel cars for the first time. So we have really managed to shift into that direction of electric traffic, at least for the private car traffic. So that's really a cool development, and it's been happening because the government was investing very much into support for this transition. And it's not only supporting people buying, it's not only the government supporting people buying, it's also the government forcing the importers of the cars to co-fund. So there is a co-funding scheme of those companies and the governments for this transition. And you can see on this very detailed list how it works. So there's sums from a few €100 to 20,000 euros, depending on the case and car and setup that is being paid. And the government doesn't only fund the cars; it also co-funds the charging infrastructure, which is one of the main issues, especially when we think about hydrogen fuel systems. Then the kind of infrastructure is way more important. For the electric vehicles, it's not so much; it's way cheaper. But still, the government funds this transition too. And you can see that there's a differentiation between the usage, private business use, and there's a big differentiation if the infrastructure is public or just privately used. So the funding is very different. And this seems to have worked out really well. And I'm currently in the next phase of rollout of funding. So I'm working on, what's going on? Too much for PowerPoint. Okay, seems I need to restart the presentation. Sorry for this. Okay. Am I here? Yeah, okay. So I'm currently working on programs that support the transition of public transport and also heavy-duty vehicles and infrastructure. So we are currently trying to get organizations working with public transport transitioning to battery, to emission-free vehicles, be it battery electric vehicles or hydrogen fuel cells, or and we just closed the first call. We have enough interest, so it seems to be a very successful project. And there's another follow-up program that funds the transition to emission-free emission-free heavy-duty vehicles and infrastructure that opens this late summer fall. And the government is pumping about €500 million into these programs in the next 3 years. So there's a ton of money going out to individuals and companies working in those areas. And it's essentially co-funding. So we are paying a share of the added costs for these emission-free transportation vehicles. So we don't cover everything. We just cover a certain amount of the added costs that it needs to go for the sustainable transportation modes. And so the programs will run for the first 3 years and then will be extended until 2030. So there's additional funding coming in. And this is all following the Austrian 2030 Mobility Master Plan that tries to pave the ground and gives a framework for the decisions that ministries are taking to roll out those fundings. So we try to avoid emissions without sacrificing the achievements that we have. We try to shift into emission-free traffic whenever possible, and at the same time improve the systems and make them more efficient. And the way this is laid out is there was like a visionary approach for the year 2040 that was taken, thinking of this year as all land transport modes are decarbonized. All the green energy used for transport is generated sustainably within the country. So those are the kind of preconditions. And then it was like thinking back from that goal to the year 2030. Where do we need to be there if we want to be at this big goal in 2040? So it's kind of a backcasting approach that was taken. And it's also, if you take this approach, it's really interesting to look at certain things. For example, the kinds of traffic that you need to deal with. So if you look at passenger and freight transport, at the same time, you can see that freight transport is growing on a much higher rate than passenger transport. So what you need to do as a government is to really subsidize what's going on in freight transport to have a bigger impact. And that's exactly what they're doing. So things like that are laid out in this big strategy. And there's also this goal of changing the modes of traffic, to change the modal split within those actually few years towards more public transport, towards more walking, more bicycle, more use of bicycle, to really encourage people living in cities to walk and use bicycles. There's this concept of 15-minute cities. I don't know if you're aware of this. So that you generate an urban design that everybody living in a city can reach the essential other places within 15 minutes of walking. So there's concepts like that that are supported, and try to make use of the traffic technology or drive technologies in a better and more efficient way to go for, as I said, walking and using the bike, and just limiting the use of not so efficient transportation modes to where we actually really need them, and support these emission-free technologies wherever we can. So to sum it up, we want to have 100% of all new cars and vans registration as zero emission no later than 2030, hopefully earlier. 100% of all heavy goods vehicle registrations should be zero emission by 2030, which is really ambitious. And 100% of all new heavy goods vehicle registrations will be zero emission by 2035. So that's kind of the promise of this new concept. And I'm really too happy to work in this. I feel that we are moving something along. And with this, I want to thank you for your attention. And I want to thank the members of my lab, some of them are still here, for their great work, and the organizations that have funded my work and collaborated with me. Thank you.
Okay, thank you, Petra. Do we have any questions? Okay.
Thank you, Petra. I really enjoyed the origami project. To see a lot of potential there. I'm wondering what models of electric vehicles you find in Austria. Are there a lot of European manufacturers doing the electric vehicles, or are there
yes,
imports? Okay.
Yeah. The problem at the moment really is to get the vehicles, because there's so much disruption of the supply lines that it's really hard to get things delivered in time. So I think that's the biggest issues at the moment. Yeah. And in Austria, we look, I mean, there's no restriction for the manufacturers. I think many of them come from many other German, but yeah.
That was really great. I'm thinking back to the leaf tiles and papers, and it's making me think back to the fractals yesterday. And I wonder if you guys were able to talk at all, but thinking of kind of fractal borders on those and how that would change the performance.
Well, yeah, we have looked at fractals, but it seems that there are certain sizes that are interesting, and there's a scale limitation. So the scaling of those functionalities comes with the boundary layer size, and the boundary layer size is again depending on the air movement situation and on many other things. So it's kind of, that there's a kind of basic physics scale to the whole system that is still poorly understood, I would say. So Ariana has a background as a designer and an engineer, so she managed to understand this kind of basic physics phenomena. For me as an architect, it's really hard. I don't have this kind of background. And as far as I have understood, it's still not entirely clear how this whole system functions. And in leaves, it's way more complex. You have this internal humidity, this whole internal space where the humidity actually is generated and then comes out through those leaf pores. So the system is way more complex than the crude biomimetic mock-up that we did use. But it's a first trial to go into this direction. And I'm really curious what the BioCool project will have as an outcome. So I hope that they will finish the project in time in fall. And I'm really curious if they will be successful in getting something out of it.
The leaf design, have we considered looking at the leaf design as like the fins on radiating systems for air conditioners or car engines, or is it just being used mostly for like roofs at the moment?
Well, the principle can be used for any kind of heat transfer device. So that was actually the first idea, to just use it for a technical heat transfer device. And because of my background in architecture, I pushed for this direction because this is a problem that I'm very familiar with in a context that I know very well. But I think it could be applicable to any kind of cooling device where shape is interesting and where you can live with humidity. Many of them don't want to have humidity. So that's the other thing. Can you live with humidity in your system or not?
Petra, thank you. So we're curious, what was your first stakeholder buy-in? When did that occur? How did it occur? And how do you think we can use that, or what key should we use in moving North America towards this model too?
About the leaf research or in general? I don't really...
Just in general, about creating the mobility.
I've been in biomimetics for so long, I have difficulties answering this question. So for the leaf research, I think that, for example, GAF was triggered by the presentations that we did. So the roof company, they really were interested in this principle because they thought it could be beneficial for their product range. At the same time, they also see a lot of problems that come with using water in their materials. So it's something that they, worked with for a while. I don't know if they have taken it further. So usually my experience with companies is that they get very interested when they have problems. And that's also why we started working with the aerospace industry early on. So we worked with ESA, for example. So the European Space Agency was actually the first company that funded one of our workshops when I worked at the Vienna University of Technology, because there are so many unknowns with design for space that's a really interesting source of innovation. So I think where there's issues and where there's big questions, then biomimetics or biomimicry is an interesting methodology to find answers. Did this answer the question? I'm not sure.
Yeah, and I think another one of the questions they were curious, what was the most impactful part of this journey for you?
The most impactful part of the story for me? I have no idea. It's super exciting, all of it. So I've been doing this for a very long time for a reason. So I always had this kind of genuine interest in design and biology. So I'm fascinated. Thank you.